Welcome to this course on statistics. Statistics is the science of making decisions under uncertainty. It is a collection of processes and philosophies about the best way for collecting, summarizing, and analyzing data so that we can make inferences. Mastering the foundational concepts of statistics with the ability to read and interpret statistics will help you through any career. This is particularly true as an analyst, BI specialist, or business leader. And for a data scientist, a strong foundation of statistics is core to the job. This course introduces the landscape of statistics and concepts needed to run simple statistical tests and interpret the results. This knowledge will support you in conducting good analysis, applying data to business decisions, and in exploring more advanced topics in other areas of data science or machine learning, like those in our more advanced beta program courses. We recommend this course for anyone without any background in statistics, or for those who want a refresher. Though we will assume some basic knowledge of mathematics, such as how to calculate a mean. As you go through this course, you'll use both real and simulated data sets to apply what you've learned using Excel's data analysis tools. This will allow you to practice these skills hands-on and quickly with easily available software and with relatively large data sets. Let's get started. Statistics is the process of collecting, summarizing, and analyzing data so we can make decisions or inferences. Statistics is a really broad umbrella term. It can cover a lot of different methods, formulas, practices, and different theories. To better understand statistics, it can help to break down the landscape, and that is the goal of this chapter. We'll define and illustrate a few different types of statistics and approaches towards making inferences. First, we'll define descriptive versus inferential statistics. Then we'll explore the three big approaches to inferential statistics: the classical, frequentist, and Bayesian approaches. Finally, we'll look at a flowchart that can help us start to think about when we should be using descriptive statistics, when we should be making the jump to inferential statistics, and when we might want to use a machine learning approach. Through this exploration, we'll introduce some foundational terminology, which will make navigating more complex conversations about statistics easier in later courses. But, eventually, we hope you'll be able to use your understanding of the landscape and of the tools available to deconstruct a statistics problem into a course of action. Here is my data. Here is the decision that I'm trying to make, so what are the best tools to apply? Let's get started. We need to cover some important dataset terminology up front. Understanding these terms will be important as we move through this course. First, a dataset is the collection of data that we have to work with for our statistical analysis. A simple dataset might be stored as a table in an Excel or a CSV file. Though, more complicated datasets might have data stored in databases and across multiple tables connected by relationships. Or it may be stored using other approaches like graph databases, used for purposes like social networks. For this course though, we'll stick to datasets that are captured in a single table, like the one that you're seeing here. Each row of our dataset represents a single observation or event. It describes data we've collected about a single individual, like a specific person or place, or a single event, such as the outcome of a dice roll. In this table, each observation looks at tree saplings 1 year after planting. In our columns, our dataset also contains variables, or features. These are the inputs we have that provide information about the observation. So for each tree, we have a variable that tells us a variety of data about the tree and its environment. For example, we can see the slope of the terrain that it was planted on. The variable that we want to predict, estimate, model, or just better understand is referred to as the target variable. This is often an important metric for our organization. For this example, we're really interested in the tree's mortality at the end of the year. It takes quite a bit of resources to plant a tree, and that investment is lost if a tree dies. Finally, datasets often have a unique ID, which helps us to identify each row or observation. Stepping back, it's important to remember the total dataset that we work with is a sample of a population. With this dataset, what we're really interested in is making inferences generally about planting certain varieties of tree saplings within a large region. We are curious to understand these saplings in any year, current or future, and across a variety of environments within that region. In this case, we cannot obtain a complete sample of our population. I can't, for example, get data about the survival of next year's trees, nor can I afford to measure every tree or visit every place in the region. So, we have a population, the set of events that we're trying to make inferences for. Then we have our sample, the set of events captured in our dataset. With statistics, we'll use the sample to make inferences or predictions about the larger population, and those samples need to be representative in order for this to work. This is something that we'll explore in more detail later on in the course. So, we have a dataset about tree saplings here, and we want to apply statistics to this dataset. At first, maybe just to explore it and see what we discover. Like, how does this year compare to the previous year for survival rates? Or we may have a specific question that we want to ask of this data. Like, why is this year's survival rate lower? Statistics has specific tools and methods that can help us with any of these questions, and many more questions as well. Broadly speaking, there are two big categories by which we can lump statistical tools or methods. These are descriptive statistics and inferential statistics. Descriptive statistics help us describe or summarize the observations in our sample. Descriptive statistics take thousands of individual observations and provide us with an output that can be used to summarize it. We can summarize the central tendency of our data with a mean, median, or mode. We can summarize our data with measures of dispersion, like the range or variance. Or we can summarize the shape of the distribution of our data with measures like skewness or kurtosis. Since descriptive statistics just summarize our data, they're objective measures. If everyone has done their math right, we should all agree about the exact mean of a variable across our observations, and there really shouldn't be any disagreement about its shape or variance. Now, a limitation of descriptive statistics is they only tell us about the sample that we're looking at. I may know from my dataset the average mortality rate of a tree was 0.67, but I don't know the mean for trees outside of my sample, those in regions that I didn't record, or next year's set of trees. This brings us to our second big category, inferential statistics. Inferential statistics aid us in making inferences about a population from our samples. In some approaches, you might see this inference summarized as a probability, or a p-value, or a percentage chance, or margin of error. These are our two big areas within statistics: descriptive statistics, which summarizes our data, and inferential statistics, which makes inferences from our data about the population. Inferential statistics is where we'll be spending the bulk of our time in this course, and in other courses where we look at statistics. Of course, knowing how to summarize data with descriptive statistics is a really important skill and something worth spending time on, and we will. But when it comes to data science and being a data scientist, this is the science of making decisions under uncertainty. And to do that, we need a nuanced understanding of the tools available to us under the umbrella of inferential statistics and how to apply them properly. Before we continue, there's something that I said in the last lesson that I want to go back to. In some approaches, you might see this inference summarized as a probability, or a p-value, or a percentage chance, or margin of error. In some approaches. And this brings us to something I hope you take away from this chapter. That is, there are many approaches when it comes to inferential statistics. When it comes to descriptive statistics, data scientists mostly pull from the same few dozen tools and they'll agree on the outputs. But with inferential statistics, there are both a lot more tools and a lot more opportunities for two different data scientists to produce two different conclusions. there is sometimes less agreement, which isn't always a miscalculation or a fluke, but often just a difference in approach. Overall, there are three big approaches to assigning probability in statistics. First, there is the classical approach. This approach works by assuming each possible outcome has a set chance of occurring. If you've ever had to calculate the odds of rolling a 6 on a regular 6-sided dice, you'll be familiar with this approach. Before you even roll the dice, you can divide 1 by 6. You'd find the probability of rolling a 6 is 16.67 repeating percent. You are not relying on observations. You simply calculate the probability based on the assumption that each side of the dice has the same chance of being rolled. Second, we have the frequentist approach. This approach instead focuses on observed outcomes. Frequentists determine probability by looking at how often specific events occur, generally under carefully controlled experiments. So, to find the odds of rolling 6 on a dice, we simply roll that dice over and over and over again, and then see what happens. An underlying principle is that as the number of observations in your experiment increases, the accuracy of your predictions increase. Your observed probability will, generally, move closer to the real probability as your sample size grows. So with this approach, a large dataset is preferable. If the dataset is too small, the prediction often just becomes insufficient data, or we failed to reject the null hypothesis, which is a way of saying there simply isn't enough data, and there's an uncomfortably high chance the result may be due to randomness or noise in our data. If you roll a dice 3 times in a row, and each time you see a 6, is that because the dice is weighted, or is that just by random chance? From a frequentist perspective, the average mean so far is 6, but they would caution that the dataset doesn't provide enough information to let them confidently claim the dice is weighted or different from normal dice. As the dice is rolled more, they'll get closer and closer to the real probability. They'll never know exactly the probability, but eventually they'll get close enough that the error becomes insignificant. Finally, there is the Bayesian approach, and this approach is subjective in that it allows us to build in additional information, such as prior data, personal opinions, models, or additional knowledge that we may have. At the core, Bayesian statistics is still incorporating observed data, but it allows itself to be influenced by additional factors. We see this approach used in YouTube recommendations. YouTube's algorithm might start from the belief that you want to see the most popular videos in your geographical region, but then it will update recommendations as it learns more about your preferences and viewing habits. And every new piece of data that it collects about you is used to update its probabilities about if you might like to see any specific video. As we said earlier, it's possible for 2 different statisticians to come to 2 different conclusions. The assumptions that are used within the approach that they choose is an important factor that might create such differences, and those approaches each depend on certain underlying assumptions being met. Part of the job of a data scientist is to ensure that the assumptions are suited to the approach being used. For example, imagine asking 2 different statisticians to weigh in on which of 2 finalists will win the World Rock, Paper, Scissors Championship. One statistician assumes that there is no inherent skill or strategy to rock, paper, scissors. So, for that statistician, the odds of one player winning is going to be 50-50. Another statistician might notice that one of the players is left-handed, and historically, left-handed players win 62% of matches when facing right-handed players. That statistician might therefore assume that the odds are higher for the left-handed player. Either of these approaches may be appropriate if the underlying assumptions that led them to choose this approach is true. If rock, paper, scissors really is just a game of pure chance, then the classical approach of assigning a 50-50 chance makes sense. If left-handed players really do have an advantage, then it's not unreasonable to build a model that incorporates this information to adjust the odds in favor of left-handed finalists.
We can even imagine a third statistician who might try to get the two contestants to run some trial games in an environment similar to the environment of the final match. They'll have the finalists play and collect observations of how often each player wins or loses. I think most people would see this third approach as fairly objective, but again, there are underlying assumptions that have to be true for this approach to do a good job. We are assuming we can control the environment so it's truly comparable to that real match. In reality, one player might feel more pressure when the real match occurs, and their performance might change. And we're assuming that their skill level is constant. In reality, players may gain skills or new strategies as they play more games. After 50 games, player 1 might notice that player 2 always twitches their thumb before throwing scissors. This approach assumes a consistency between each game that might not exist. So to recap, there are three big approaches to inferring probability: the classical, the frequentist, and the Bayesian. And those approaches each depend on certain underlying assumptions being met. Part of the job of a data scientist is to ensure that the assumptions are suited to the approach being used. Statistics is a toolbox for data scientists. It is filled with a variety of different tools that we can apply to solve problems, make decisions, or gain new insights. As a data scientist or a data analyst, a core skill is being able to identify the appropriate tools for the job at hand. When presented with data, you will need to consider if it makes sense to rely on descriptive statistics for your analysis, or if you're aiming to make decisions that will require the use of inferential statistics. Even then, if you're using descriptive statistics, you'll then need to decide which descriptive statistics make the most sense for your data. Does a mean better represent the middle for this dataset? Or should we use the median or mode instead? If we're going beyond that and using inferential statistics, we'll need to decide on our approach. Do the assumptions of the classical approach make sense? Is our dataset controlled enough and large enough for the more rigorous frequentist approach? Then, after we've selected the approach, there are a large variety of tools and methods that we can apply that fit under each approach. We can't even begin to list all of the options available, much less cover them in detail. Later in the course, we'll explore one of these methods, hypothesis testing, and we cover other advanced methods in our more advanced courses. Let's step back and run through a flowchart that is intended to help you think through which tools are best. To start, you have some data. If it's new data to us, we might not even understand much about it, how it's collected, what the variables really measure. So we can start to explore that data through exploratory data analysis, descriptive statistics, basic visualizations, and maybe talking to those at the source of the data. And this might be as far as we need to go at this point. Then we can ask ourselves, are we making any decisions with this data? If we're not, then we can use descriptive statistics. At this point, we can use what we've learned so far to inspire us, or find some insight to take away. Maybe we discover something interesting, like survival rates went down for most species of tree last year, but for some reason, that didn't happen to the species of spruce trees. As long as we're not drawing any big conclusions or making any decisions from that data, this is just fine. But let's say that you do have a decision that we need to make. We should next ask, how many decisions? If we have a lot of small decisions, well, we might want to look at machine learning. Machine learning processes are really great at making a lot of small decisions very quickly and automatically. Perhaps we can make something to help planters on the ground decide what mix of species to plant, based on the conditions of that area and on that day. If we have just one decision to make, we should next gauge how important this decision is. If the decision isn't too important, well, maybe we can go back to descriptive statistics and see if we can find something there that can help to guide us. Maybe we just want some data to help us pick a tree for our home garden. Data can help inspire us, but we shouldn't bring in the data science team just for that. Inferential statistics take time and cost resources that not every decision deserves. Now, if what we have is a big, important decision, something where there is a lot of risk involved, and we're willing to spend some resources to get to the best possible outcome, decisions that may affect the long-term strategy of our organization, for example, that's a great time for applying inferential statistics, so that we can make the best decision possible given the data and the resources that we have.